Ladies and gentlemen, class recording started. So, yesterday we introduced the last section of chapter 5, and that deals with friction. And we introduced first that friction is a resistance force. It opposes the motion of one surface over another. Friction is always opposite. It always acts against something or opposite of something. A lot of times it's motion, but we'll see later today that that's not always the case. That sometimes we can have friction even though there is no motion. Yesterday, we introduced the idea of kinetic friction. And kinetic friction is encountered when surfaces slide against one another. Kinetic friction is the friction that acts on moving objects, right? That's generally what most people think of when we talk about friction. We're dealing with things that are moving, in opposition to that moving object. And we talked about some of the things, some of the properties of kinetic friction yesterday. We also talked about the relationship between kinetic friction and normal force. That the normal force acting on an object, right, this blue arrow that points upward, is related to the amount of frictional force that an object feels. And that relationship is summarized by this term, which we called the coefficient of kinetic friction. The coefficient of kinetic friction relates for us how much frictional force an object actually feels in a situation based on the normal force. And over here on the right, there's a table that shows the relationship between a couple of different surfaces. Right? I think we talked about the idea that if we look at the coefficient of friction relates to the surfaces that are involved. But the actual force of friction depends on the objects in a given situation. Julie, go ahead.
Do we need to know this table?
You do not need to memorize that table, no way.
So we don't need to put on our notes?
No. In any problem that I give to you, I will either ask you to solve for the coefficient of friction, or I will give you the coefficient of friction to use in the problem. Okay? And we'll see how we're going to do that here in just a second. Okay? Yeah, please do not waste time on your note card putting that table down. So. All right. On the next page is an example problem that puts together these ideas of kinetic friction and then the coefficient of kinetic friction and how it affects a moving object. So, it says, pass the salt, please. Always manners, right? Says someone at the other end of the table asks you to pass the salt. Feeling quite dashing. I mean, I really wish I would have wrote that. I didn't, that's why. It says, you slide a salt shaker with a mass of 50 grams in that direction. The shaker slides with an acceleration of 0.787 and comes to rest at the desired location. It says, what is the coefficient of kinetic friction between the shaker and the table? So, to start, what is this question asking us for?
Coefficient of kinetic friction.
The coefficient of kinetic friction. So we said we use this Greek letter mu, right? Looks like a U, but it's got a little tail on it, right? The Greek letter mu to represent the coefficient. And in this case here, we're talking about the coefficient of kinetic friction. So we use the subscript K. That's our unknown. On the previous page, we just learned that the coefficient of friction is a relationship between two forces, right? What two forces does the coefficient of friction tell us about? The kinetic friction force and also the normal force. So, if we're going to solve for the coefficient of friction, we need to know these two forces. So these two forces are technically also unknowns in this problem that we need to get our ultimate answer, right? So we need to know that the coefficient depends on these two forces. So to find the coefficient, we got to find the two forces. Okay? Other things we know. What else did they give us?
The mass.
They gave us the mass, right? So it says with a mass of 50 grams, right? That was a terrible line, but so we know that the mass is 50 grams, but do we want it in terms of grams? Do we want it in grams? We want it in kilograms, right? So we move the decimal point 3 places to the left, and we end up with this many kilograms. And then it also tells us what? It also tells us an acceleration, right? An acceleration of 0.787. Okay. Now, just because we've encountered this situation before, or a situation similar to it, what would we actually see happening with this salt shaker? Physically, what would we see happening to it as it slides across the table?
Accelerating.
It's going to slow down, right? So we would probably call this acceleration what? Probably call this negative acceleration, right? As it relates to our situation right here. Okay? Good there. All right. We've identified what we're looking for. We have identified what we know. Now there's a picture to help us out, okay? So first, I'm going to add to this picture your hand that you used to push the salt shaker across the table, okay? It's over here because you pushed it away from yourself, right? And because of what you did to it, this salt shaker is now moving, right? Look at all the whoosh lines. There it goes, okay? All right. Now, even though the forces are drawn on there for us, the way that they've drawn them, I'm not really sure helps us analyze this motion as well as it might be. So I'm going to draw over those forces and just put them in terms of things that we've done so far, okay? So if we start identifying the forces that are acting on the salt shaker, what can we do first?
Normal.
Okay, well, let's go somewhere else besides normal. Let's go gravity first, right? Because normal force is kind of hard to draw in on its own. It sort of depends on other stuff, right?
Yeah.
So let's draw on those other things first, okay? All right. So we'll call it, right, we know that this is gravity, okay? And we've already done a lot, right? We know how to calculate that force of gravity, yes? Okay. In order to calculate the force of gravity, we do what?
That times the acceleration of gravity.
M times g, right? Okay. Do we know the mass in this problem?
Yes.
We do, right? Do we know g? Right? So we can plug that in and we can find out what the actual force of gravity is acting on this problem. And then, okay, we'll cut it off at that spot so it doesn't get too big.
But if you know the mass and acceleration, you can find out the net force.
Yes, but hold on. Hold on with that. Let's take this in order here. Let's finish this picture first, okay? Okay. Julie, go ahead.
The one that has all the forces, is that the one that you're pushing towards the person, or the one that, like, when you land down?
This picture, just to clarify, this picture shows the salt shaker as it's sliding, right? And then eventually over here, it comes to a stop. So that's like two pictures of the same salt shaker in two different spots.
So the later one is the one
The
where
late,
it stops?
the later one is like it stopped, yes. Okay.
Then why would
So,
I'm
yeah.
confused with how the acceleration arrow.
I don't know.
is.
I would not put that acceleration arrow there. I would put it over here. Okay. But another thing too, Julie, I wouldn't put that acceleration arrow on this picture because this is a picture that's supposed to show us forces,
Okay.
not acceleration. You know what I'm saying?
Yeah.
So sometimes the picture they give you, it can help, but if you're not really familiar or you're not really 100% certain what it's showing you, it can be a little bit confusing.
Okay.
Okay? So yeah, I'm going to stick with forces in my picture and go from there. Okay? All right, so we got this gravitational force, right? Maxie, where can we go next?
Normal.
Let's go normal force, okay? We said normal force comes from the surface, right? In this case, that surface would be the table. So normal force is going to go up in this direction here. All right, we'll label it F of n. And then one more force, right? What else would be acting on this salt shaker as it slides across the table? Okay, this is going to be a friction force, and Nina specifically, it's what kind of friction?
Kinetic.
This is kinetic friction because the salt shaker is doing what? It's moving, right?
What's a kinetic part to it?
That's the movement part, right?
Well, I can't you just say the, like, force of friction?
That's what we did yesterday when you weren't here.
Yeah.
So, that's your responsibility to figure that out.
Okay.
All right. We'll see why a little bit later today as well. All right. So we got these forces, okay? Now, two things about this picture. First, we have three forces drawn in our picture, but only one of them is labeled. Can we label another force before we move forward? Let's label the normal force, right? Julie, what's the normal force going to be in this problem?
0.49.
The normal force in this problem is going to be 0.49. Why, Julie?
Because they're proportional.
Yes,
For the-
why? You're right.
It's
I
not-
just wanted to explain it a little better.
Uh,
What did you just, what did,
Some of it.
it's not accelerating which way? Down or up, right? So on the y-axis, what do we have to add up to?
0.
0, okay? And that's why it is, right? Now, somebody asked before about normal force, right? We can't make the assumption that normal force is always equal to gravity. It is in this case because how many forces are we dealing with on the y-axis? Just 2, right? So in this case, normal force would be equal to gravity, but that's not necessarily always the case. Okay? Cal, what were you going to say?
No, I was just gonna say that's being included.
The one you said before, though, before we started talking about normal force. Okay. In order to get this salt shaker to start moving, right, to slide it across the table, this hand has to push it and give it an applied force. But that applied force has not shown up on this drawing. Is there an applied force acting on it in this direction? As soon as that salt shaker leaves the hand, there is no forwards force. The hand only pushes forward on the salt shaker when it touches the salt shaker. As soon as it leaves your hand, that force isn't there anymore. But the salt shaker still moves forward. Why? Because of its inertia. Your hand started it moving forward. Inertia tells it to do what? Keep moving forward until something makes it stop. That something is currently in the process of making it stop, right? But it hasn't completely made it stop yet. So the moral of this story being, when you draw your free body diagram, there doesn't necessarily have to be a force in the direction that that object is moving. You have to analyze what's going on at that situation. This salt shaker is moving to the right, even though there is no force to the right, at least at this very moment. Okay? Good there? All right. So moving forward, this is an accelerating object, and we can analyze an accelerating object with which equation? We've only written it like 100 times in the past week, right? Sigma F equals m times a, right? Newton's second law to analyze this accelerating object, okay? What did we say the sigma meant?
Total.
The total, or the sum, right? How many forces do we have in this picture? 3. So sigma F, F of G plus F of N plus FKF all together equal m times a. Right? Now, make our lives a little easier. We're not cheating, we're just using prior knowledge, right? We have written down that 3 forces make up the net force in this problem, and that's true. But what have we already established about 2 of those forces? Those two of those 3 forces cancel each other out. So we can just kind of go, okay, let's just forget about those 2 right now, because we already know that they cancel each other out, right? And now the net force is completely caused by the kinetic friction force. The acceleration in this problem is solely the responsibility of the frictional force. Does that make sense? Okay. All right, then we start plugging in things we know, right? That's good that we have an equation to solve for the kinetic friction because we said kinetic friction was one of the things we needed to know to find the coefficient of friction. So in this case here, right, if we know the mass, which we do, and we know the acceleration, which we do, we can figure out what the kinetic friction force is. Is that what it is?
Would you round?
What is it exactly? I can't remember.
.03935.
Okay, 0.03935. We'll keep it like that. All right. Good there.
Is that the answer?
No. Well, that was my next question. Is that the answer? What did this question actually ask us to solve for? The coefficient, right? We just learned that the coefficient of friction depends on 2 things. It depends on the force of kinetic friction, but also it depends on the normal force. So we start plugging in things we know, right? Okay. We just learned that the kinetic friction force was negative 0.039 newtons. Earlier, we figured out that the normal force was 0.49 newtons. And we end up with that, if I remember correctly. Is that right? All right. Let's talk about this answer just a little bit. Okay.
Can you keep it just 0.08?
Technically, we probably should have 2 sig digs on it. Actually, we should have 3 sig digs on it because all of our other measurements had 3 sig digs.
Okay.
So, 0.080, I think 2 was the next number.
So it
was
was
it?
0.07959.
Okay, because you guys rounded it a little bit. All right. Then it would go like that. That would be 3 sig digs, right? Okay. Yeah, we rounded it a little differently doing it this time than I did last time. So, all right. So let's talk about this answer a little bit. First, that is the coefficient of friction. Okay. In order to find the coefficient of friction, you divided the frictional force by the normal force. Force divided by force. Newtons divided by newtons. If we have newtons on the top of the fraction and newtons on the bottom of the fraction, what happens to our units there? These units cancel. The coefficient of friction does not have a unit. It is a unitless quantity.
What?
Yeah.
Doesn't everything have
Because it's not a measurement. It is
Oh,
a
it's
relationship between 2 forces. Okay? So, it is a coefficient, it is not a measurement. Alright? Second, when we do this math, it comes out as a negative number. That's okay. The force came out as a negative number because the negative is just telling us what?
which way?
Which way? The coefficient doesn't have direction. Okay? It's not a measurement. It's not a vector quantity. So, if you left it as negative 0.08, I would give you credit for that on the test, no problem. But in actuality, there is no such thing as a negative coefficient. You just sort of disregard that number, or the negative, because it doesn't mean anything, and that would technically be our answer. All right, so one last thing before we move on to the next part. I told you earlier that the coefficient of friction relates to the surfaces that are involved, but the actual force of friction relates to the specific object in the situation that we're dealing with. So let's say this problem changed so that instead of having 50 grams of salt, there was 100 grams in that salt shaker. Would the answer to this question be different?
Yeah.
No. Because the coefficient relates to surfaces. Even though we put more salt in this salt shaker, it's the same glass salt shaker on the same wooden table. The coefficient would remain the same. But these numbers would all be different. Okay? That's the difference between the coefficient of friction and the force of friction. They're two different ideas. The coefficient relates to surfaces that are involved. The force relates to the actual object we're talking about in a given situation. Okay? So keep that in mind, that the coefficient doesn't depend on what actual object we're talking about. We're talking about surfaces. If we go back to the one example from before, we talked about there was a, on the chart, the top one here is rubber on concrete. That's basically your tires on the road. Your tires on the road have the same coefficient of friction regardless of what car you drive, because the surfaces are the same. But your compact car has a different force of friction than some big SUV, because the actual objects are different. Okay? Does that make sense? All right. Let's go to the next part, and let's talk about static friction. The fact that it is
Who are
The-
these people?
Company D and Choir, they were out performing
Oh.
somewhere. So-
Interesting outfits.
All right. Static friction, because its name is static friction, right? Static implies what? It's not changing. It's still, it's not moving, it's not changing. Okay? So, if we take this book and put it on this desk, earlier in the period, we established that up and down, gravity pulls down, normal force pushes up. In this case, how are gravity and normal force related?
The same.
They're the same, but one goes down and one
Opposite, yeah.
goes up, right? They're opposite direction. But let's say I go and I push on this book like this. Okay? But what do we observe?
It's happening.
Nothing happens. Right? Yikes. Something happened that way, but so nothing happens, right? Things don't move because why?
Your applied force isn't enough, then the
Inertia.
Yes. What else does that mean? Inertia, Dylan, inertia means that it does what? It wants to stay at rest unless what? Unless something acts on it. I'm acting on it, but doesn't move, right? What else does there have to be here?
Another friction is
Another force. Which way?
opposite.
The opposite way. This is the kicker. How big?
Equal.
It has to be equal,
That's weird.
all right? Because that would make the net force what? Zero. Okay? Static friction, like it says up here, right? Static friction acts to prevent motion from starting. Okay?
I thought friction is based on the surface, correct?
Yep.
So, like, the only thing I don't understand is if you put a little bit more force and it still didn't move, that means the friction and force would be more. So it's like screwed with me.
What we find out is that static friction, the force of static friction, can have any value from 0 to a well-defined maximum. If I push on this book and it doesn't move, it's because there's a frictional force that acts in the other way just as big to make the net force 0. If I push harder and it still doesn't move, what had to have happened to the frictional force?
More.
Had to have gotten bigger. Because what does the total have to be? 0. Can the frictional force just keep increasing to match any force that I apply to this book? If it did, Julia said no, she's right. Okay? If it did, what would never happen? Nothing would ever move. Because friction would just keep balancing out whatever force I apply, and we end up with 0. So here, let me show you this picture. I apologize for not putting this picture into your packets. Sorry. Here is a picture that shows applied force on the x-axis and frictional force on the y-axis. The first part of this graph is labeled the static region. If you look along this red line, what's happening to the x values along this red line? They get bigger. What happens to the y values? They get bigger as well, just as much. So in this section right through here, what is the net force? 0 the whole time, regardless of how hard, regardless of if I push this hard or this hard or this hard, friction is this big or this big or this big to completely balance it out until we get here. As you can see on the y-axis, this is labeled Fs max. Why is that an important value that we have to know?
Because that's when it changes.
Force that it takes to get it moved.
That's the force, that's the greatest force that friction can apply while it's standing still, right? And if we go back to that section from the book, right, down at the bottom, it says, the maximum static friction, a stationary object begins to move when the applied force equals the maximum force of static friction. All right? There's a problem with that sentence, though. What's the problem with that sentence as it is written? There's one word that we have to change in that sentence.
Great.
Equals can't be the case. If your applied force equals the maximum static friction, the net force is still what?
0.
0. So here, we got to change this to begins to move when the applied force equals the maximum force of static friction. We should change equals to what? Greater than, or how about it exceeds? Ooh.
Too big for me.
Hi, Juliet. Juliet, if you have like 3 minutes, this class is almost over.
Oh, yeah.
So,
Okay, bye guys.
so, stationary object begins to move when the applied force exceeds the maximum force of static friction. Okay? So, we got to have a way to figure out what the maximum force of static friction is. All right? Guess what? There is a coefficient of static friction, just like there was a coefficient of kinetic friction. Okay? The coefficient of static friction, we still use the Greek letter mu. Okay? But this time, we're going to use the subscript s for static friction. Okay? It's still a relationship between two forces. Normal force still goes on the bottom, but now what force do you think is going to go on the top? Static friction, so FSF, right? But specifically, which static friction value do we want?
Max.
The maximum static friction value. That's the important one, because we have to exceed that value if we are going to make anything happen. Right? So the coefficient of static friction gives us the maximum static friction value, or we can use it to find the maximum static friction value, and that's important. If you look, I think next slide down on your packet, right? This table compares the kinetic friction, or coefficient of kinetic friction, with the coefficient of static friction. Okay? What are you seeing about the static friction coefficients versus the kinetic friction coefficients?
Greater.
They are all greater. What does that tell you about moving an object?
That you could, like, I get it, because you know how it went up and then it went down a little bit,
Okay.
stationary? It's because once you exceed it, you actually use less force to move it.
So that means
It takes more force to get an object to move, and then inertia takes over.
it takes more force to get an object to start moving than it does to keep it moving once it already is moving. All right? You may have experienced this, like if you're moving like furniture, like a couch or something across the carpet, right? If it's really heavy, to get it to go to begin with is generally harder than once it is to keep it going once it already is moving. Because the static friction that it feels to prevent it from moving to begin with is greater than the kinetic friction it feels once it already is moving. Okay? Good there. All right. Tomorrow, we will talk about moving this jack-o'-lantern across the table by attaching it to a bucket full of sand. Why we wouldn't just pick it up and move it, I don't know, but that wouldn't be as good a problem. So,
Forgot it was Homer Day.